Welcome to the Pacific Northwest Geodesign Forum. I'm Tim Nyergis, Professor of Geography and Director of the Masters of GIS for Sustainability Management. I'd like to take this opportunity this morning for thanking you all for signing up, registering, being here this morning at this early hour. Hopefully a number of other people will arrive in due time, as it would be. And I'd like to take this opportunity to acknowledge the sponsors of the activity. This event wouldn't occur, at least the students, for there is a free lunch in the world every now and again for students. Students didn't have to pay a registration fee. So the 4 colleges from the University of Washington came together, or at least units, I should say, from 4 colleges came together. The College of Arts and Sciences with the Department of Geography and the Division of Social Sciences, the Master of GIS Program for Sustainability Management within the Department of Geography. From the College of Built Environments, we have Landscape Architecture and Urban Design and Planning that are part of the Planning Committee. From the College of Engineering, we have Civil and Environmental Engineering. And as engineers sometimes, as it would be, I'm a geographer, a would-be engineer as the case would be, I think, all these years. The engineers sometimes have a little bit deeper pockets. They didn't even want to bother to go to their dean for money because they had enough to contribute themselves. So that was quite nice for the faculty to get together and do that. From the College of the Environment, we have the School of Environmental and Forest Sciences. And last but not least, the National Science Foundation funded project that's called the Cyber GIS Project. It goes by the formal title of Software Integration for Sustained Geospatial Innovation.
All right, great. Well, our next presenter is Dr. Michael Flaxman, and he has taught at the Massachusetts Institute of Technology's Department of Planning for 5 years. And his primary research interest is the use of spatial simulation modeling in the planning and design of cities and regions. He's particularly interested in the development of tools for stakeholder-based planning that present evaluative models in the context of using visual simulations. He's practiced GIS-based planning in 17 countries, including 1 year as a Fulbright Fellow in Canada. Dr. Flaxman previously served as an industry manager for architecture, engineering, and construction at Esri, and prior to joining Esri, he was a lecturer in landscape planning at Harvard's Graduate School of Design. He received his doctorate in design from Harvard University in 2001 and holds a master's in community and regional planning from the University of Oregon and a bachelor's in biology from Reed College. He's widely considered to be one of the thought leaders worldwide on geodesign, and this morning he brings us a tour of geodesign tools and methods. Michael, welcome.
Thank you. Thanks. So as some of you noticed, I have some Pacific Northwest heritage in my bio there. I originally learned about watershed planning thanks to David Holtz and the University of Oregon. So what I wanted to do today is just go through a little bit the relationship between kind of the way in which geodesign is conceived and the tools that are used or needed, and talk about a couple of ways of thinking about the tools, and then present a kind of quick and broad and over-the-top summary of some of the existing tools and kind of where we are, where we're going to close it out. So caveat up front, this is necessarily an incomplete view. As I started preparing this talk, I realized how much stuff is out there, even for me, and I've been looking at this stuff for a while. So I'm just going to cover some of the more widely known and widely used tools. I'm purposely omitting some of the great tools that are going to be discussed by others in the forum today. So if you don't see your stuff up there, that's the only reason. So stepping back for a second, there are a wide variety of definitions of geodesign that are out there, and most of them are useful. The most terse, of course, is my old Harvard advisor, Carl Steinitz, who says it's just geography by design, which is amazingly terse. But then when you have to unpack it and try and implement it and figure out what that means, you end up coming with long-winded definitions like I did a few years back. And so my version's a little more technical and significantly narrower. I called it a design and planning method which tightly couples the creation of design proposals with impact simulations informed by geographic contexts. And so that came straight out of the work that I had been doing for many years and observed others doing, where there was this constant need to try and tighten up the cycle between proposing an idea and evaluating its consequence. And the fancier the evaluation of that idea, the harder it was to get the ideal, which would be real-time feedback in a public meeting kind of context. So I was always gunning for this notion of tight coupling, getting stuff really dynamic so that it could be used and even follow a public conversation. That's a kind of high bar for a lot of big models. So that's why I use tight coupling as opposed to trying to claim it needs to be real time, for instance. But increasingly, obviously, the IT infrastructure we're all using is headed that direction. So by the broader definitions, almost all conventional GIS and CAD systems and even non-digital tools could often be considered geodesign tools. If you're using the principles of looking at the surrounding context in your design, okay, a lot of it's going on in the designer's brain, but sticks and mud can be used as geodesign tools, really. So at that level, it's a kind of ethical design method. It's more described by its goals than by its techniques. On the other hand, I prefer to stick to my earlier definition because it gives me something to hang on to, which I find useful. So the two questions I usually ask myself of a lot of systems that I see are they tightly coupled? And do they include impact simulations that are informed by the geographic consequence? And again, informed by is a little bit of a wiggle. So it doesn't mean that there's a buzzer that goes off when you exceed the stream flashiness rate. But it means you're really getting substantive design changes based on that feedback. And if you're not, then I'd argue, well, it's not really geodesign. Maybe it's environmental impact statements where you write a 400-page report or 4,000-page report, and few people read it, and a few months later you get some notes back and you change the thing. Yeah, that's geodesign as done by lawyers, right? But hopefully we can do better than that. So one of the key things up front is that a lot of stuff, if you start dealing in the world of design, you realize really quickly, particularly those of you like me with a science background, that one of the challenges is that design methods may or may not start with explicit goals. Often they have only implicit goals. And the narrower of these really are just accommodate use X legally while minimizing my cost. I need this building on this site, please build it and keep it cheap. That's the worst end of the spectrum, but it's fairly common. That's 90% of the landscape out there, arguably. So in those, the systems that support that kind of work and thinking are really articulate about the client goals. So you get cost estimates of every doorknob, right? And you've probably all seen BIM or building information models that generate, the list of parts that go into your design. On the other hand, the public interest and sustainability side of things is only considered, if at all, relative to legal requirements. So am I actually in the floodplain? Am I violating the law on the setback? Really narrow version. And the second part of my definition, informed by geographic context, I left out the kind of the motivation behind that, but that kind of implies a non-trivial representation of the context area. And for a lot of those cases, if you know GIS, it kind of implies GIS, really, because you don't want to be drawing in every feature of the pre-existing environment in order to evaluate a design. You want to be able to use what's known from the worlds of science and from remote sensing to start off with some reasonable knowledge of the pre-existing conditions. So it's a very different view of pre-existing conditions, by the way, a kind of science view of pre-existing conditions instead of a blank piece of paper with a polygon that is the site parcel. And that is still the most common starting point for a lot of design. So that's really this slide. I mean, if you start your design work with a piece of paper and your parcel boundaries floating in paper space, really hard to get in environmental information of any kind. Where's the closest school? Is it overcapacity or under? What's the demographic of the neighborhood? What's the watershed upstream and downstream of what I'm thinking about? All that stuff is really hard if you're going to be doing it yourself. If you embed things within a geographic context, you can get a lot of that for free or almost free, right? Just give me a georeference and the scale of your site, and I know where you are in a watershed. So basically, the contrast between geodesign methods and prior design methods that's the most important from the perspective of the design community is that it really implies a couple of technical things. One is that all design needs to be georeferenced. And I'm kind of putting that out there as in normative terms, but there's no reason not to design things in georeferenced context. But again, 90% of the work done out there is not done this way. If you do that, then you get substantial ability to do better work. But it doesn't automatically give you the rest. And so the second piece in terms of technical requirement, which is very hard coming from the CAD and building design frame, is the ability to compute or request computation of, if you think client server, of the design plus context. So you have all kinds of design systems that, again, can give you nth degree of detail about the doorknobs in the building and have no idea whether the site is flat or sloped or which way the water drains. So the notion that you want to be able to compute on context data means you need something more than an orthophoto. It's not enough to have a visual representation of the background of the site and then assume that the designer is going to be able to do a good job. A good designer can do a great job with just an orthophoto. But again, that's kind of not geodesign except in the very broad definition. That's geodesign in the designer's head, with the technology not really doing anything to support it other than displaying an orthophoto underlay. That's not great. Second major point to make about thinking about these different tools is that there are clearly relationships between spatial scale and methods, and there is a spectrum of scales that all of this work needs to be able to accommodate, and it ranges from very fine scale, single parcel, fairly detailed design, all the way to conurbanization of state scale, or multi-state scale, if you want to think about the Northeast conurbanization. So clearly, if you're dealing with conurbanization at state scale, you don't want to be drawing things. It's just infeasible to draw at that scale. On the other hand, if you're doing just a site, it's clearly the way to go is to drive things from the ability to draw. And then city scale is kind of in the middle, depending which way you're coming from. And the tools that have developed over the years support a range of methods for dealing with data input. A lot of the work starts with drawing or sketching and geosketching, but there are a number of tools that are designed for dealing with broader scale that offer some form of picking, either from a uniform tessellation like a grid, and I'll show examples of this in a minute, or watersheds or other predefined units. And so, it simplifies the task if you're dealing with very large areas to be able to pick units instead of drawing them. But of course, you're generalizing the geography. You're saying, this arbitrary number of activities is occurring somewhere in this geography. I don't know where, but somewhere in there. And then finally, at regional scales and above, it starts to become unreasonable to either draw or to pick. And you need methods to simulate, for instance, urban growth. And I think we'll have some talks on at least one method for that later. But that range of capabilities is needed in there somewhere. So one of the kind of ideas behind the software of ArcSketch and now in what Bill Miller has been working on, the GeoPlanner app, is the notion of what I've termed geosemantic sketching. It's kind of a $10 word for a fairly simple idea. So the idea was we wanted to avoid this kind of cumbersome process of first digitizing raw geometry, then adding attributes, then computing characteristics, and then computing impacts, and just make it very simple for people to start by picking a kind of rich symbol, which set up a whole set of object or class characteristics that you could pick residential as a category off a map, and you can infer a lot of stuff from somebody picking residential. That concept is not proprietary, and many web tools, for example, would still benefit from using it. So there's actually room for this idea to spread still. You still sometimes see web interfaces or other interfaces where people have to draw a polygon first and then say what it is, and then run things manually as an impact assessment. So just the very notion of tying this together and making it easy to get an immediate inference from something you're drawing, I think is an important first step. As mentioned, there's then you have to follow on with kind of how are you going to deal with urban growth outside of the specific site or the specific thing that you're working on, or climate change, to go back to the last talk. And in some cases, you can use sketch versions of that. But in many cases, particularly broader, you're going to want to bring things in from plans. And that bringing things in from plans or other data layers can really be done in two fundamental ways. And so the one that gets a lot of attention, it's really easy to do, but it gets a lot of attention because it's scary, but it's scary in part because it's not very accurate, is build-out analysis. So you just take the county's current plan and you say, what if we developed everything the county says is developable? Develop to the hilt, right? Really easy because it's a spreadsheet calculation, not realistic at all. And the realism of it, though, by the way, varies by scale. So for a site plan or a little community neighborhood plan, if it says 10 acres of residential, you're probably going to get 10 acres of residential. But at the very broad scale, you're unlikely to get very far with build-out analysis. So then you need some kind of ability to simulate. And the kind of variation in the tools that are out there, there are a bunch of tools that simulate kind of what I'd call agglomerations of built form. So simulate things at the zone level. There's going to be residential here. Can't tell you exactly the form, but more or less looks like this. Versus tools that are increasingly using parametric methods to attempt to simulate siting across very large areas. And I think we're going to see some work from the City Engine group, which is right along these lines. So that's a kind of new level of ability. Planners really have never before had that ability to simulate tangibly what a set of buildings might look like or a development footprint might look like writ large across a city. So as I mentioned, there are kind of two general ways of thinking about organizing these sets of tools. And one is by chronology. And so this could be a talk in itself. So I'm not going to go there very deeply. But a lot of the tools fundamentally come from the idea of analog map overlay. So it really goes back to early landscape architecture in the late 19th century. And people manually drafting things with, over light tables and figuring out what was dark and light on the map. And amazingly, that idea still actually has currency today. The other example I usually try to pull out of history because it's a little fancier, Ian McHarg, in his study of Woodlands, Texas, back in the 60s, did that, but he also did something most people don't realize, which is he used the universal soil loss equation, sorry for the acronym here, and a TR-55 calculator, one of these old HP reverse Polish notation calculators, the high-end tool of the day. But they computed water runoff curves for that particular site, and they based the zoning on the characteristics that the runoff that they wanted. So instead of the normal way, which is here's the zoning I want, let's go figure out the watershed impacts, he took it completely the other direction and said, here's the watershed and the performance characteristics I want from the watershed, and drove it backwards into the zoning. Well, that still today isn't done very often, and it's a good idea. But a hard idea. The third historical example that I mentioned is, again, more recent history, but you'll hear probably several times in this conference, if not a dozen, ecosystem services. So there has been a lot of work over the years in trying to characterize the economic benefits of natural systems. And some of the earliest work in that was software that was, at the time, an ArcGIS plugin called CityGreen. And it was designed to look at the impacts of urban forestry on particularly stormwater outflows. But interestingly, it was designed using a lot of feedback from mayors and town councils. And so they found that instead of quantifying the watershed impacts in scientific terms, they needed to quantify them in mayoral electoral terms, which basically meant dollars of cost avoided. And that turned out to be actually a pretty smart method. Even 30 years later, you can have your beef about different kinds of ecosystem services applied to endangered species. There are a lot of hard cases. But quantifying the cost of avoiding doing something really stupidly is still a really useful method. And usually attention grabbing, like we saw in the last talk. You can come up with really big numbers because conventional ways of doing things add up to really, really expensive. To give credit where it's due, there are a series of what I'm calling mature digital tools. So these are tools that we looked at when we were first doing the original geodesign work at ESRI, and they were out there, I think, already at the time. So these are kind of the mature suite, and I'll show examples of these three in a minute. But basically, some of these tools have been out there for a decade and longer, and of course, because of that, have been, significantly refined. And then it's both fair and unfair to compare those to some of the cutting edge or bleeding edge research prototypes, some of which we may see today, or I'll show you an example of something we're up to. Those things, haven't had the test of time or the refinement, but are able to use some of the more recent technology. In taxonomy terms, so the second major way of looking at these tools, basically there are a whole set of these that kind of cluster together with the notion of impact simulation. And so this has this huge tradition from engineering and from all kinds of sciences that aren't really design-oriented per se, but they can take any set of parameters, sometimes a text file that you have to enter by hand in some magic model-specific format. In fact, often that way. But it's a design if you want to think about it that way, if you want to use it that way. And so a lot of the work on spatial decision support tools, for instance, that's a 30-year-old tradition and lots of examples. Those are tools that allow you to simulate at the scenario level. And when does a scenario become a design or design become a scenario? Well, it's actually kind of ambiguous. So a lot of those tools can be used pretty effectively, and that method is kind of lurking in a lot of current tools. And then some of those things some of the impact simulators try to be really general purpose, and I'll show you some examples of them in a minute, and others are super single purpose. So I'll show you NatureServe Vista. All that does is quantify biodiversity, but it quantifies it to the hilt. So there's that question also within these tools. Is it a general purpose tool that you can do pretty much anything with, or is it really focused on one domain? So that's one cluster I found. Second one are basically impact simulators with implicit geography. And so I talked about this concept earlier, but there's still a tremendous number of tools where they give you an orthophoto underlay and they expect the designer to do something sensible. So I'm not really going to go show you many examples of those because they're so common, but that's still maybe the majority of design tools out there. And then there's some early tools that have the ability to sketch with semantics, but not to do embedded evaluation. And so the ArcSketch tool that I did with Bill at ESRI early on was able to do the input, but not the processing and output side, which is why it was early work. And then finally, and most interestingly, there are a set of more creative design tools that are coming out, and I would put City Engine, for instance, in that class. And those are tools that embed not only the ability to do impact assessment, but to actually specify design or modify or change design as a result of an impact assessment. So that, to me, goes right back to McHarg. That's saying the zoning density should be based on the hydrology. So give me the hydrology so I know what the zoning should be. So let me generate design concepts from the science, as opposed to figuring out how badly I'm mucking up the system, which is the kind of shorthand version of impact assessment. Oh, I screwed it up really badly. Well, maybe I shouldn't do quite so badly. Pull back from that. So generative design is kind of flipping that on its head and saying, let's start to use these tools to inform design more deeply. So with that quick visual survey of some of the main tools, Community Viz. How many of you have heard of Community Viz, out of curiosity? Okay, almost a third of the room. It's been out there for the longest. It was originally funded by the Orton Family Foundation, and now it's got its own separate organization. It does scenarios, as you can see, kind of 2 example scenarios, and it does interactive or semi-interactive bar charts that are all related to computed indicators. And it is pretty general purpose. So it's advertised as an urban growth modeling tool, but it has a kind of formula builder underneath it. You could use it to do stream flashiness without too much trouble. It is limited, however, in that it can only really do build-out simulation. So on the urban, broad-scale urban side, if the problem gets big enough, i.e. beyond county scale, Community Viz starts having trouble, basically because it's weak on urban growth modeling. So it does build out, but it doesn't do a great job at urban growth, in my opinion. And some people heroically have used it to do multi-county studies, but it's heroic. It's really was designed for doing small town growth, and that's what it's best at, small, medium community planning. Similar in age and history, Elliott Allen's index software, which is now has a new cloud-based reincarnation called Spark. Sorry, I forgot to put Elliott's name in here, but this is Criterion Planners out of Portland, Oregon. And very similar idea. In this most recent implementation, it's webware, but you can create scenarios, you can select particular areas to modify, and the pull down is showing that you can create a polygon, or you can do takeoffs from a line or a point, or you can grab a polygon from a plan. So the 3 methods I mentioned really does not do urban growth simulation, but in terms of manual methods, it's got them. And then Elliott has spent his career developing really good urban index indicators. And so the strength of this tool is on the depth of the urban assessment tools. So walkability and similar concepts. NatureServe Vista, I mentioned earlier. This is a good example of a really deep tool in a specific narrow sector. So this does biodiversity impact assessment, and that's all it does, all it wants to do. They were fairly unfortunate with the naming. They named this before Microsoft came out with Vista. But product software marketing person's nightmare. Anyway, it's a great tool, but narrow. Envision Tomorrow is the latest incarnation, 3rd incarnation of a tool done by Fragonisi and Associates. Originally, many people are familiar with a project called Envision Utah. This tool, it has evolved from letting you select squares to letting you draw polygons. So interestingly, they started off kind of characterizing neighborhoods. I forget the size of their squares, but they had one size of squares for the universe. And now looks a lot like the other ones I've just shown you. Digital entry of different neighborhood types, on-the-fly calculations of housing mix, job mix, acres of land consumed, etc. Calthorpe has just recently been working on and just released, I guess, Rapid Fire, which is the latest generation of what they called previously their urban footprint analysis. This is a very spreadsheet-heavy, for better and worse, version of these kinds of tools. And so you do a little bit of stuff in GIS, and here you are picking grid cells. Sorry. So you can kind of see these relative to the size of parcels. You're characterizing a neighborhood by picking grid cells, right, at a kind of mega block level. And then it's really deep and really rich in the spreadsheet side of things. So it's a nice different take on impact analysis. And last and probably least system I've been working on, so I have a kind of consulting-based company that builds software behind the scenes. And so I've been working on interactive impact assessment in terms of species habitat impacts. And so my problem in the first case was I had the state of Florida to deal with and a project that had 800 miles of beaches. Beaches you can't even see at this scale. So I needed some way to both visualize and compute on the fly the expected impact for a whole variety of species, 16 species across 800 miles of beach. And it turns out I had 100 experts, and they were all over the state of Florida. So you have these kind of custom bespoke software applications also being developed. And I would count them as geodesign, but they're not commercial market tools. They're kind of consulting plus custom solutions. So in conclusion, all the cool kids are now doing it, i.e. geodesign. And I think I showed you even briefly over the top. There's a weird West Coast bias in this stuff. It seems like every major West Coast planning firm has either its own software tools or is using software tools. And the East Coast is lagging behind, I think. So that's a challenge to Sasaki and some other ones out there. But basically, this is becoming standard practice in planning, which is a very encouraging sign. The initial challenge, really, 5 years ago, 10 years ago, if you'd asked me about this stuff, the challenge was tight coupling, because we had no systems that let you design and get an impact back out quickly. And the response, in most cases, was integrated applications, tightly integrated applications. Ironically, I guess, that brings up the new challenge, which is now interoperability. So, for instance, myself, I'm neutral to all of these tools. I'd like Fragonesi's transit planning stuff, and I'd like nature serves biodiversity. And I don't care what Calthorpe has to say about biodiversity, and I don't really care what NatureServe has to say about urban planning. I want the best indicator and index for each item. But right now, because the tools are so tightly coupled, I can't pull the index from one kind of thing from the design tool. So, you know, that's the challenge. Now we have smoothly integrated tools, but they're still hard to pull apart. So I think that's kind of the challenge going forward, basically to open up this world of indicators and evaluations. Really important to realize that science keeps moving, keeps changing, and so we'll always be behind unless we get ahead of this thing. And then secondly, the old version of planning is get a number of people in a room and hash it out. My experience across the country is a professional practice is moving to a kind of hybrid online-offline model, and we get 10 times more people participating online. And right now, their participation online is really narrow and really not very useful. So a lot of this stuff, as it hits the web, is going to have hundreds of people to thousands of people generating plans. And if that's going to happen, you really do need to be able to separate the process of designing and drawing plans from the set of impact evaluations. All right, so that's all I had for you. Thank you very much.
We've got a little bit of time here before our coffee, lemonade, water break. If you have any burning questions for Dr. Flaxman?
Yeah.
One time I did a Google search for any place in the United States that I looked at. I'm wondering if it's something you can model. If the growth is always scenario model, then scenario model
Yeah, it's a good question, a challenging one. So there are some tools from up in Canada that explicitly use the growth carrying capacity concept. I'm blanking on the name just because I'm on stage, but group out of UBC. So there are some tools that do that explicitly. I'd say in general, a lot of the tools embed McHarg's ideas, which aren't really carrying capacity so much as avoiding vulnerability. And so most of the tools are vulnerability avoidance. And then I'm currently working with ESRI and a group called Biomimicry on an attempt to merge a couple of concepts, one of which biomimicry basically says, learn from nature and get design performance standards from nature. And so what we're trying to do in that work is, again, going back to Ian McHarg, really, but it's taking design performance characteristics from natural systems, applying them back onto urban systems as a standard, a performance standard, which isn't quite carrying capacity. But the challenge with carrying capacity has always been, and it almost goes back to the origin of that formulation, is carrying capacity with which technology and in which configuration. And so if you just assume traditional worst/standard practices, then you can do a carrying capacity model. But I guess a lot of the work and current attention is in changing design, right? We're sitting in a LEED building, and you can critique LEED, but at least that standard has pushed the market forward and pushed design. So a lot of the current tools try to fairly characterize design performance, but they're fairly neutral in terms of the issue of growth versus lack of growth or redevelopment, with the asterisk that redevelopment is still really hard in most of these tools. So most of them aren't nearly as good at doing redevelopment planning as they are at doing greenfield. Again, it's kind of biased embedded from the market. So the tools are driven by the market, and historically there's been a lot more greenfield growth, at least in the US. As that starts to turn, hopefully we'll get more tools that can handle redevelopment as well.